Definition of a common logarithm. A common logarithm is a logarithm with base 10. We write log of a to represent log base 10 of a. So realize, we may not have a base written on there, okay? But if there's no base written on there, assume it's a base 10. So in this case, let's notice the log base v of a equals k, and we can convert it into exponential format, b to the k equals a. So for a, we have log, and it's log base 3 of 3. Well, let's realize that since log base 3 of 3, we're taking the log base 3 of the 3. It's kind of like multiplying and divided by the same number once again. So they're equal and opposites. So this one's fairly easy, fairly straightforward. In other words, they cancel each other out, giving us just a 1. So technically 1 is our answer. But likewise, we could always convert it that way we can double check our answer. So real quick conversion, let's bring down or copy down our formula from the top of our page. Highly recommend you write your formulas at the top of your page, that way you can see them when you're working on your homework. So let me bring it down, there we go. And now let's realize our base is 3 and our a value is 3, agreed? So if we have 3 to the k equals 3. How many times do we multiply the 3 to get a 3? Well, it's already a 3. So in other words, we can say it's a 1, an exponent of 1. 3 to the 1 is just 3, agreed? There we go. And notice that even though we don't show on the right side there, there's an exponent of 1 that we can show on there, but technically we don't have to. So let's go to the next one then. B. Log base 6 of 1. Well, let's see. We could probably convert this one as well, agreed? 6 to what power will give you 1? Oh, that's tricky, right? Well, it's not as tricky as you think. Be aware, what's the only exponent that will give you a 1 no matter what number you have? That's where a calculator can come in handy if you have a hard time remembering this, right? Turn on your calculator, clear anything you might have on there, and let's say we have in this case 6 to the power of, let's try 1. If we try 1, it gives you a 6 again, right? Anything else will give you a larger number, but we need it to be equal to 1 in this case. So how about we try 6 caret key and then try a 0? Does that bring back a good memory about which one it is? Remember, it's the easier one, right? Anything to the power of 0 is 1. So 6 to the 0 is 1. So there is our answer for this case. We know that in this case 6 to the power of 0 will give us a 1. So therefore let log base 6 of 1 is 0 by definition in that case. So C then in this case, log, and it's log base 8 of the square root of 8. Notice that it has a square root on there, okay? So similar to base 10, we don't write the number 2 on there, agreed? So base 10, we don't write the base 10 on there. We assume it's a base 10 if there's nothing there. So in this case, since it's a second order for square root, number 2, right? Let's convert this to make it easier to see, easier to solve. So log base 8 of 8 to the 1/2. It's the equivalent of saying square root. This is an exponential form, agreed? And now that we have converted this root into exponential, let's convert from logarithmic to exponential format. So the base is 8 and it's equal to 8 to the 1/2, agreed? Well, this might not be as hard to see as before now, agreed? Now that we have a conversion rather than using it as a square root format, it's now really easy to see. The only thing that I'm missing is 8 to the power of 1/2 has to be the same as the other side of the equal sign, agreed? So therefore, log base 8 of 8 to the 1/2 is 1/2. Do remember, base 8, so log base 8 of 8 cancel each other out, and leaving the 1/2 as a multiplication. 1/2 times 1 gives you 1/2. So there it is. We've shown it in two different formats, but in a sense, we've shown it in just one particular format conversion. We converted it. Okay, so let's go for the next one, D. And let's realize that log of 0.01 implies it's base 10, agreed? Even though we don't show a base, we don't have to show a base. It's assumed that it's a base 10 if there's nothing present for a base. So let's rewrite it, that way we can see it, makes it easier to see that it's a base 10. But I'm just doing this for reference. Be aware of that. You don't have to convert or change or write the base. It's automatically base 10. So log base 10 of 0.01. Our base is 10. On the other side, we're going to get 0.01, but that's kind of hard to see, agreed? Let's see if we can convert it into a much more useful value before we can convert it into exponential from the logarithmic original. So log, we have log, and we know it's base 10 because there's no base, agreed? 0.01, remember you can convert that into a fraction. Let's see, there is a 1, so we can write a 1 on top, and there's a 0 and the 1, two numbers after the decimal. So that makes it 1 over 100th, agreed? So there is our fraction equivalent. Okay, or likewise, you could probably use your calculator as a quick reference as well. Let's see, 0.01, let's hit enter. Let's go to math, fraction, hit enter. And then I'll convert it into fraction, 1/100th. There it is. It's equivalent. So it's definitely true. Agreed. We just checked with our calculator. But now let's continue with this. So now we can convert it. Converting it, 1/100th. So log base 10 of 1/100th. So that's equivalent in exponential form. 10 to what exponent will give us 1/100th? Well, keep in mind it's a fraction. The 100's on the bottom. So we would have to take the 10 and do the reciprocal, meaning it would have to be a negative exponent. So how many times do we multiply 10 to get 100? 10 times 10 was 100, right? So that means twice. So it would be 10 to the negative 2 in this case. So our answer would have to be negative 2 because it's a fraction, it's a decimal value from what we began, agreed? So originally our decimal value, let's convert it just for reference, that way we can see it. 10 equals 0.01, our base was 10, right? So we write 10 equals 0.01. 10 to how many powers or how many times do we multiply the 10 to get a 0.01? What's a fraction? It's a decimal value in this case, so we would have to convert it to a negative exponent. So it would have to be a negative 2. And likewise, you're welcome to try on your calculators, agreed? So calculator, let's see. If we have 10 and caret key, right below your clear button is your caret key, open parentheses. Use the negative sign right next to your enter button. Do not use the subtraction button. It's the negative sign. So negative 2, close your parentheses, and it should give you 0.01, which it does. There it goes. Or likewise, remember you have a log button. Push the log button. So log button on the left side, right next to your number 7 keypad, log of 0.01. Close your parentheses and hit enter. It gives you a negative 2. So your calculator actually does the work for this one. So be aware of that. We're doing just extra work, but it's just for reference. That way you can learn to see that it's true and how it works. But otherwise you could do this in your calculator. Likewise, we could do the next one in our calculator. Log of 100. So log of 100. Close your parentheses. And that gives you positive 2 because it's a whole number. Agreed? 10 times 10 is 100. So now let's see the work behind that one. So the work behind that one, we have log of 100. Keep in mind, once again, just rewriting so you can see it's base 10. And we convert it. 10 to what power gives us 100? You'd have to multiply 2 i's, right? So 10 times 10 gives you 100. So 10 to the power of 2. So our answer is, in this case, log base 10 of 100 is 2. And there's our answer. Do be aware of that. So let's see. We found or run into some common logarithms or some logarithm properties. So let's do a quick overview of those. Just a real quick one. Logarithm properties. For b greater than 0, b not equal to 1. A, log base b of b equals 1. And that's the first one we realized. Okay, it cancels out, right? When you have a log of the base of the same number, in this case b, they cancel each other out, giving you a 1. And b, log base b of 1. Well, the only number that can give us a 1 is a 0. So when you power it to the 0. So log base b of 1 is 0. Let's see. Though that would be our first 2 examples there, agreed? Our first 2 examples, when you have the same base of the same number, it gives you 1. When you have, in this case for b, we said 6 of 1, log base 6 of 1, the only thing we could use was an exponent of 0 to give us the 1. So a and b match to the properties that we were working with here, or looking at here, I should say. So a logarithmic function, base v, is a function that can be put into the form f of x equals log base v of x, where b is greater than 0 and b cannot be equal to 1. So something to be aware of. So we can use exponential functions from now on. Let's be aware that for exponential functions, our domain. So domain. In general, the domain of a logarithmic function is a set of all positive real numbers. What is the domain again? Well, the domain talks about x, agreed? So look at our graph there. If you try graphing y equals log of x. So let's try that real quick in our calculator then. Well, let's clear this out and go to y equals, and let's push the log button and put x in parentheses. Log of x. And let's go to zoom, and let's do a zoom standard, option 6. There it is, and there's the exact same thing as what you're seeing there. Looks like it stops going down on the left side, agreed, but if I go to zoom and then do a zoom box. Let's see where my cursor is at. I'll move it. There we go. There's where my cursor is at. I'll hit enter here. Since it looks like from here on I can't see anything graphed, right? And I'll move it so that I can see close to the y-axis here. There we go, probably around there. I'll hit enter, and it looks like nothing was being graphed. But look at that. There is something being graphed, but it's just so close to the y-axis that we can't see it. Let's try that again. Zoom box, and I'll graph it even closer to the y, that way we can actually see, otherwise it's going to be difficult. I'll hit enter. Notice that it looks like it stopped up above, but it's really continuing to graph. We just can't see it because it's so close to the y-axis. And I'll continue from there. There we go. So now do you see that it's still continuing to graph? And if I continue zooming downwards, it'll still show me a little bit more of that. So I'll go to zoom, and I'll try to zoom out. Let's see what it looks like as I zoom out. There we go. And now look at that. If I continue to zoom out, you continue to see more. Zoom out, you continue to see more. Eventually, it looks like it zooms out of its way. So I go to zoom, do zoom standard, option number 6. That way it's a little bit more intuitive. There we go. That looks more like what we have here. So once again, we just realized that our domain, well, doesn't go past the y-axis. So hence the reason why it says it's all positive real numbers. So domain, all positive real numbers, agreed? So we have all positive real numbers for our domain, and therefore, rough sketch there for you, the red line down, implying that it suddenly plummets down, straight down, essentially. And it never reaches the y-axis. Remember the word asymptote? A value that it has never reached. In this case, our y-axis becomes our asymptote. Reciprocal of exponentials, right? Where the x-axis is the asymptote. Something to remember. Okay, and let's look at the range. The range of y, well, it plummets down extremely fast, right? So it means it goes down forever into the negative y values. And it goes up, but it slows down. But it still continues to go up forever, very slowly. So in that case, we can say that it's all real numbers in that particular value for the range. So the range, all real numbers. And big arrow to show that it goes up, but slowly. So backtracking real quick into your original expressions or equations. There we go. Just so you can get a sight of this once more. So once again, keep it in mind. If you have a log that has no base, it's a base 10. And we call it a common logarithm with base 10.